One crushes entire stars with ease. The other spins 700 times per second and blasts out beams of death. Which one wins? Today we're throwing the universe's most extreme objects into the ultimate heavyweight bout. In this corner, weighing in at 4 billion solar masses, the black hole. And in the other corner, packed into just 20 kilometers but spinning like a cosmic tornado, the Neutron Star. We'll break down their strengths, weaknesses, and mind-bending physics in 5 epic categories. Let's get ready to rumble. First up, who has the strongest gravitational pull? Black holes have something called an event horizon. Think of it as nature's point of no return. Once you cross this invisible boundary, not even light can escape. The gravity is so intense, it literally warps the fabric of space-time itself. Imagine stretching a rubber sheet and dropping a bowling ball on it. That dent. That's what a black hole does to the universe. Neutron stars? They're nothing to scoff at either. A sugar cube of neutron star material would weigh about 4 billion tons. That's like having Mount Everest compressed into a tiny cube. But even their incredible density can't match the gravitational monster that is a black hole. Fun fact, did you know some supermassive black holes can begin tearing a star apart in less than a day? That's like eating Earth for breakfast every morning for a year. A neutron star packs about 1.5 times the mass of our Sun into a sphere just 20 kilometers wide. We're talking about cramming Manhattan's population into a single grain of rice. The matter is so dense that protons and electrons have been squished together to form neutrons, hence the name. A single teaspoon of neutron star material would weigh about 5.5 times 10 to the 12th kilograms. That's a 5, followed by 12 zeros. It would instantly punch through Earth and out the other side. Black holes? They're actually less dense overall. Yeah, I know you thought black holes would win the density contest too, right? Wrong! Sure, they have incredible mass, but their event horizon can be enormous. Some supermassive black holes are less dense than water when you consider their entire volume. Plot twist, right? But the fight's just getting started. Both of these cosmic titans are born from the same violent event, the spectacular death of massive stars. When a star runs out of fuel, it goes supernova, one of the most energetic events in the universe. But what happens next depends on the star's mass. For black holes, if the star starts with more than about 20 to 25 times the mass of our Sun and its core after the explosion is over about 2.5 to 3 solar masses, it likely collapses into a black hole. The core implodes into a single point called a singularity, where the laws of physics as we know them break down. For neutron stars, stars between 8 and 25 solar masses can collapse into neutron stars, depending on how much mass they shed during their lives. The collapse happens so quickly in just seconds that it creates a shock wave that blasts the outer layers of the star into space. What's left behind is a city-sized ball of pure neutrons. This round is a tie because, despite different endings, both start with the same dramatic stellar death scene. Now let's talk about how far these cosmic monsters can reach to cause havoc. When black holes feed, they create accretion disks, swirling vortexes of matter being torn apart and superheated to millions of degrees. These disks can span light years and shoot out jets of radiation that travel at near light speed. And let's not forget spaghettification, the process where tidal forces stretch you vertically while compressing you horizontally. Sounds fun, right? Neutron stars have their own special brand of destruction. When two neutron stars collide, they can briefly create conditions hotter than the center of any star, forge heavy elements like gold and platinum, and send gravitational waves rippling through the universe. But in terms of reach, black holes win, Their gravitational influence extends much further, and they can influence space across vast distances, shaping galaxies and devouring anything that strays too close. Fun fact, as of 2024, the nearest known black hole to Earth is about 1,500 light-years away. The nearest neutron star, only about 400 light-years, but don't worry, neither is coming to visit us anytime soon. Some neutron stars become pulsars, cosmic lighthouses that emit beams of radiation while spinning hundreds of times per second. The fastest known pulsars spin 716 times per second. If Earth rotated that fast, we'd all be flung into space. Then there are magnetars, neutron stars with magnetic fields quadrillions of times stronger than Earth's. These cosmic magnets are so intense they can bend atoms, and if one passed close enough to Earth, it could mess with chemistry and electronics. And here's something wild. Neutron stars are the universe's most precise timepieces. Their rotation is more stable than our best atomic clocks. We use them for navigation in deep space.